Okay, welcome to tutorial number 19. We are going to be working on the context part of our quad unit. And here we go. Starting in 1965, the number of youth softball teams in the U.S. could be modeled by the equation S equals 0.075 t squared, where S is the number of softball teams in thousands and t is the number of years after 1965. Find the year when there was 60,000 teams. So that's a lot of words, right? And so what we're going to do with these these word problems, these context problems, is we're going to try to figure out how to make them manageable. And so we read it through the first time. That's always a good strategy. And then we're going to go back through and note things. We note, first of all, that they give us the formula. Okay, so that's the first step. That's what we're going to do, is we are going to write the formula down. Because there you go. And then we look at the formula and we say, wait a minute. There's two variables. We don't know t and we don't know s. That's not good. So then we're going to keep reading the problem. We see that find the year, it says find the year when there was 60,000 teams. We're like, okay, what do we do with that 60? So let's go back and see. S stands for the number of softball teams, and then we're put in thousands. And I know you've seen this before when you've read data and charts. You can't always write out 60,000, the number, or 60 million, if we're talking about population. And so we just say that the number is going to be represented in thousands, and then we just put how many thousand. So they're telling us S is the number of softball teams. And here it says find the year when there were 60,000 teams. So that's going to be our next step. We realize we can plug 60 in for S. And then before I go ahead and pull the rest of the thing down, our work is done here. We know that we can, almost with our eyes closed, right, because we've gotten so good, we can solve this quadratic equation. This is the square root one. So I want you to go ahead and pause the video and go ahead and solve this. Pick up a calculator if you don't have one already. And then come back after you're done to check your work. Okay. Hopefully your work looks like my work, except for you might have stopped here, right? Because you solved, you divided both sides, you took the square root, and you said, oh, I got two answers, that's great. But if you're not thinking and you stop there, that's going to be a problem, right? So that's when I went ahead and separated. I said, well, either t is equal to 28, or t could be equal to negative 28. And that's when I have to stop. When I get to the answer, each time with these problems, I have to stop and go back up and see, wait, what was t anyways? Let's see, t is the number of years after 1965. So if t is time, and I have negative 28 for time, time can't be negative, right? So time only has the positive option. So if t is 28, I'm also tempted to just stop there and say, yay, I've got my answer. But I have to remember, t stands for the amount of years, the amount of time in years after 1965. So I go ahead and add 28 to it, and there we go. There's my answer, 1993. Okay, with this next one, we see something familiar to us. We looked at something like this in our polynomial operations unit. And it says the area of the given rectangle is 30 square feet. We know that area is length times width, and that it's equal to 30. So I'm going to go ahead, and that's how we'd set it up. 2x plus 1 times x minus 5 is equal to 30. We can solve this problem. So what I want you to do is go ahead and solve it. Or if you're not feeling confident, you can kind of solve it and peek as you go. But the answers are just, we distributed, we gathered like terms, we brought the 30 over, and then we kind of got a little bummed here, right? When you reach this stage, and please pause if you're not to this stage, we reach this stage and we realize we can't factor, we can't factor out a 2, We can't set up our two parentheses, so we're forced to use the quadratic formula. Once again, the new stuff is just talking about how to set up the problem. So this is the new, how to set up this problem. The rest of the stuff we're doing is old. So go ahead and do the quadratic formula for this, press pause, and then come back and check your work with mine. All right. So here I use the quadratic formula. We got two answers. Yeah, I have to get rid of this to see the two answers. All right, so our two answers are either x is 7 or x is -5/2. So once again, the new stuff is at the beginning of the problem and then at the end of the problem. Because I can't just say, yay, I'm done, x is 7 or x is -5/2. I have to go back up to the problem and say, what was I looking for anyways? What is x? Oh, find the dimensions of the rectangle. So dimensions meaning the length and the width. So let's think about this. Let me transfer my, so 7 or -5/2. So let's transfer that up here. Oops, where'd that go?
So on this string of 4, please go to the...
Okay, so either x is 7 or x equals, and I've forgotten because I'm -5/2. All right. Only one of them is going to work. Can you see the one that's not going to work? That's right. If we used -5/2 for x and we plugged it in to the width, we'd get a negative dimension. If we plug it into the length, we get a negative dimension. That's not okay. Measurements have to be positive, right? So we know that that's not our option. So instead, this is saying when we plug 7 in here, what do we get? 2 times 7 is 14. 14 plus 1 is 15. We get our length equal to 15. And when we plug 7 in here, we get 7 minus 2, right? So our width is equal to 2. These problems are, they involve some thought, right? We have to think, we have to read, we have to understand what they're wanting us to solve for, and then when we turn to our skill of solving the equation and then using quadratic formula at the very end, we have to say, what does this answer mean anyways? And we have to go back up to the problem. Okay, Janelle was asked to solve the following quadratic by factoring. Her work is shown below. This is a different type of problem, right? This is actually you being the teacher and checking Janelle's work. So let's see how Janelle did. She saw that she could factor, and good for her. She set up this problem. We got to check the first line, right? Did she find two numbers that multiply together to equal -8? She sure did. So good for you, Janelle. But let's just do that second check. Did she, those same two numbers, did she find that when she added them, they equaled -7? Uh-oh. They don't equal -7. So that's where she made her mistake. So was Janelle correct? Let's say no. Now here's your option. You can explain in words why her work was not correct, or you can just say -1 plus 8 does not equal -7. That is an acceptable way to answer this. That was kind of fun. Being a teacher is not too bad. You should consider it for your career. It's actually a pretty good job. All right, so, and you just got a little sample of that, correcting someone else's work. All right, a baton twirler tosses a baton into the air. The baton leaves the twirler's hand 6 feet above ground and has an initial vertical velocity of 45 feet per second. Use the formula, to solve the problem. Okay, once again, they are giving us a formula, which is great. This is like the first problem. So we're going to use this formula. But the first thing we notice about it is that it's not very helpful when we have 1, 2, 3, 4 different variables to solve for and only one equation. So we're going to go ahead and read the rest of the problem to see if we can help ourselves. So let's see. H stands for the height of the object at any time. So when I think about that baton flying through the air, the height is always changing, right? It's always changing. So we can't say, it'd be kind of weird if we threw the baton up in the air and it just stuck there at 10 feet up. I mean, that would be a little freaky. So we can't plug anything in for H yet. All right, V equals initial velocity. Oh, initial velocity. I think I saw that somewhere. Yep, initial vertical velocity of 45 feet per second. So that 45 is going to match up with V. That's a constant. And then initial height, well, I saw that somewhere up here too, right? Well, I didn't see initial height, but it says the baton leaves the twirler's hand 6 feet above the ground. That's its initial height. The baton started 6 feet above the ground, and that matches up with S. Now let's talk about time. Once the baton twirler let go of the baton and it started flying in the air, time just keeps on ticking, right? We can't, time is going to remain a variable. It's always changing. So we'll go ahead and say always changing. All right, so where did that get us? That got us to taking the equation that they gave us and plugging in. I can't change anything about H yet, but I do know, let's see. I can't change anything about T. Darn it, doesn't look like I'm going to. I can change something about V, right? V is 45. It's a constant. And S is 6. So now we went from an equation with 4 variables to now an equation with just 2. So this is the one that we're going to use for the rest of the problem. So let's look at A. The twirler catches the baton when it falls back to a height of 5 feet. Okay, I don't want to give away my work, so let's see. I'm going to write right above here. If it fell back, so she already passed the baton up in the air. It fell back, and she catches it at 5 feet. That's the height. So now I can take this equation, and I have a number to stick in for H, right? I'm going to stick 5 in for H. I'm going to plug in 5 for H. And now, finally, I have an equation that only has one variable. So I can now solve for T. All right, I want you to go ahead and challenge yourself because this isn't new. Go ahead and solve for T. Yes, you're going to have to use quadratic formula, just telling you. Pause it, and then when you're done, come back and check your work with mine. Okay, that was a lot of work, wasn't it? But everything I just wrote underneath this problem is old. We already know how to do this. But when we finish and we end up with an answer, we have to ask ourselves, wait, what were we solving for anyways? How long is the baton in the air? We're solving for time. How long represents time? And that's T, we knew, represented time. Can time be negative? Can we say, man, she threw that baton so fast it was done in negative 0.021 seconds? No, time cannot be negative, at least not time as we know it now. Time can be 2.8, and is that 2.8 minutes, 2.8 hours? Time was measured in what? Let's go back and check. Time was measured in seconds. So now we're going to add the units, 2.8 seconds, to our answer. And voila, we are done. All right, let's look at this next one. If she misses the baton, how long would it take for the baton to hit the ground? So once again, we're going to go back to our original equation, this one in the blue. Okay, we're going to come back to this original equation. This time, we know that the new height is going to be 0 because when something's on the ground, it doesn't really have a height, does it? It's going to be 0. So what I want you to do, I should have thought of leaving myself a space, but what I want you to do is go ahead and take the same formula and plug in 0. Let me switch up my color so you can see it. Let's plug in 0 for the height. So I'm using that same formula that's in the blue. I'm plugging 0 in for the height. And we end up with 0 and then the minus 16t squared plus 45t, and I believe it is plus 6, right? All right. Spoiler alert, you are going to have to use quadratic formula for this. All right. You do the work, do the quadratic formula. When you're done, unpress pause and check your work. All right, so hopefully you did your quadratic formula and you ended up with different answers. I somehow switched from t to x. It's just, I guess, in my nature to just write x. But then when I'm done with my answer, I have to remind myself, what am I even solving for? How long? And we measure how long in time, right? Can time be negative? No. But time can be 2.93, and once again, seconds. I mean, that would be odd if it were minutes, right? That would mean she threw that baton so high that it took 2.93 minutes to fall to the ground. That'd be a little freaky. All right. At what time does the baton reach its maximum height? Here's where we do need some additional information that we didn't have before to find our maximum height. We know that if we think about the baton's path, here's the girl with the baton. I'm assuming it's a girl, so I don't know. We'll make it a guy. So the baton got thrown up in the air, right? It's going up in the air, and it's coming back down. This whole idea of a baton, and it started 1, 2, 3, 4, 5. It started at 5 feet. This whole idea of time going past, right? 1 second, 2 seconds. Well, we're going to have to really make this 0.1, 0.2 to make a decent graph. But this whole idea is the motion started here at 5, and it kept going up and up and up, and eventually it peaked, right? And it came back down until it hit the ground. So we're looking at part of a quadratic, right? Part of a quadratic graph. And right here is its maximum, and we know that that's the vertex, right? So a way to find your maximum height is, remember how we had A equals B equals C equals, and we had it over here. We had A equals negative 16. This was for our equation once we put in the initial velocity and the, what else? In the initial height. This was our, these were our A, B's, and C's. Well, using the same A, B's, and C's, we can find the maximum height by putting negative b over 2a. And it's part of the quadratic formula. I know you recognize that. So let's see, negative b is going to be negative 45, and a is negative 16. So when you put that together, you get what? Negative 45 over negative 32, or you could have used your calculator and ended up with 1.4. Now, what does 1.4 mean? I just found when the baton reaches its maximum height. When means time, so this is at 1.4 seconds. So at 1.4 seconds, so let's just say right now, this is 1.4 seconds, okay? At 1.4 seconds, it's reached its maximum height. So we found out when it reaches its maximum height, and that's all it asks us to, right? It doesn't ask us to actually find, let's see, 1.4. I think we're good at 1.4 seconds. Okay, so let's see what else we need to do. This very last problem, interpret the y-intercept of the equation. What does it mean in the context of the problem? So we see right here is the y-intercept, and we got really good first semester at saying the y-intercept is always our initial something, right? Maybe our initial height, or the initial amount in our bank account, or sometimes we say in the beginning, in the beginning the height was 5 feet tall. So either way, we're going to write something like that. So interpret it, the y-intercept is the initial height. It represents the initial height. If you want to go and say more words, well, we kind of have to. What does it mean in the context of the problem? Okay, the initial height, we could say, or in the beginning. You know what? Initial height's enough. Initial height is good. I'm for brevity right now at the end of the school year. Okay, I think that's it. Thank you for joining me. I look forward to you asking me questions about this, and to have fun with your practice. And I will see you in the next tutorial.